Hello, this is Mr. Rollison, and this is a video walkthrough of the test that we've already taken. It's a p12.8 in my physics class, and I want to walk you through it for those of you who want to redo it. Let's see, it's 12. I got 20 minutes to do this. I've already tried to do it once. Actually, I tried to do it twice, and nothing was working. So hopefully this time it'll work. So you got to put your name in, of course, and who cares, because I'm going to erase this anyways. So there's that. Now we get to the questions, right? This is where we hope that things actually start working. Oh, come on. Okay. Appears like it might be working today. Oh, seriously? Oh, I'm going to be very upset. All right, here we go. Gravity is the strongest of the four fundamental forces. True or false? That is false. So there's four forces. You got the strong nuclear force. You got the weak nuclear force. These are both the nuclear forces. You got electromagnetism. And you got gravity. And this is from strongest to weakest right here. Strong nuclear. Oh, I have nuclear written up there. Weak nuclear. Strongest to weakest. Weakest. So think about atom, right? Just here's a little atom. It's got two positive charges and two neutral. Those are protons and neutrons, right? And it's got electrons out here. And we're just thinking about what we know about like magnets and stuff, right? So if you have to, so I don't know if you ever push two of the same poles of a magnet together, but they repel each other, right? So in this, inside this atom, there's the electromagnetic force in here between these two protons is trying to push them away pretty hard, right? Because they're both positive charges. So there's something really strong holding them together. That is the strong nuclear force that holds that together. And that's the strongest of the forces. Strong nuclear. And then I'm not really worried about weak nuclear. That's what's responsible for radioactive decay. It sends off alpha particles and whatever like that. Don't worry too much about that. So it goes strong nuclear, electromagnetic. That's the force between positive and negative charges, or positive and positive charges, right? So that's the force that's holding the negative charged electron to the positive charged nucleus. It's negative opposites attract, right? The same signs repel each other. Negative repels negative, positive repels positive. That's electromagnetism, and that also is a lot stronger gravity because it is based on the matter and all that stuff, and it's what we experience. It feels really strong, but in terms of its actual strength, it is the weakest of the four. So the next question is also has basically the same thing. So this is the first one's false. The second one, the strong nuclear force holds the electrons in orbit. Nope, we just said the strong nuclear force holds the nucleus together. It's the weak nuclear force that not the weak nuclear force, the electromagnetic force that holds the negatively charged electrons to the positively charged nucleus. So that's false. The strong nuclear force operates over long distances, longer than gravity. No, that is false. So if the force has the word nuclear in it, if it's a nuclear force, it operates in nuclear distances, which are tiny, right? In the proton, that kind of thing. And it's not in the proton. I'm tired and I'm hurrying. It operates in the nucleus. Nucleus, geez. So the strong nuclear force operates in the nucleus. The weak nuclear force also operates in the nucleus. Gravity and electromagnetism are both theoretically operate over infinite distances. Now, their influence becomes so small, it becomes negligible really quick, right? Like we don't care about the gravitational force of stars other than our own sun, right? But in theory, these two operate over infinite distances, and the nuclear forces only operate over those tiny distances. So the nuclear force operates over long distances. That's going to be false. Two positive charges will be attracted to each other. That's false because positives attract negatives and negatives attract positives. All right, this one I'm going to have to do a little bit of explaining on. If I can get back to my, boy, this thing really just is not making me happy. An electric field projects electric force over a distance, causing an electric potential to exist in which a charged particle will have electrical potential energy. So each one of these things leads to the next one. So here's what I'm going to do. I'm going to start with, here's a charged particle, okay? That charged particle creates an electric field around it. And this isn't the normal way we draw field lines, but I think it's more natural to think of it this way. So this charged particle has an electric field around it, right? And that electric field projects a force. So in that field, in the electric field is an electric force. The electric field is the projection of electric force over a distance. And if this field is the projection of electric force, then all over this field, electric potential exists. That's potential. All over this field, electric potential exists. There's potential there, there's potential there. Anywhere in this field, there's electric potential. And then the last thing is when you actually put a charge, you have an electric charge. You have this electric charge that projects a field of electric force over a distance, which means there's potential out there. But it's not potential energy until there's another charge in it. Once you put, let's say I put a negative charge right here, now that electric charge is in what? It's in the it's in that electric field, which is projecting the electric force, which causes an electric potential to exist. And now that I actually have something that is matter, I have potential energy, because this matter is experiencing this pull, and we can use that force to what? Do work, right? Because energy is the capacity to do work. So this one here is true. All right, next one. I'm going to erase all that because I'd like to erase it all. Okay. If you can't tell what I'm doing, but I'm trying to get my marker back. There it is. A conductor is simply a material that has its valence band and conduction band overlapping, allowing electrons to flow through the material with minimum applied voltage. This is true, and let me explain what's going on here. So this is going to be, we'll think of this as the valence band right here of three different materials. This material is going to be the insulator. This material is going to be a semiconductor. And this material is going to be a conductor. So this is the valence band. So that's the outer band of electrons. Remember, if we have like a nucleus, and then we have the electrons flying around. The outer band of electrons is the valence band, the outer shell, right? The valence shell. So then there is theorized to be a conduction band that is above that, which is the band of the electron of the molecule where the electrons can flow freely. And in insulators, so this is going to be the conduction band up here. And in insulators, there's a huge gap right here. And this is the gap that an electron would have to jump over to actually be conducted. And so if you add enough energy, you can get that electron to move, but you have to add a ton of energy. In a semiconductor, you can add less energy and the electron will move up to the conduction band. And once it's up here, that means it can go travel to other atoms, other molecules and stuff. That's what the conduction is. It's the free flow of electrons. And in a conductor, the conduction band and the valence band overlap. So it takes basically no energy for the electron to get into the conduction band where it can flow freely from one material to another. So the answer to this question, a conductor is simply a material that has a valence band and a conduction band overlapping. That's true, because it's the conduction band touching the valence band that allows electrons to flow freely. The next one, doping is the process of completely purifying a semiconductor so that it can be used effectively in electronic stuff. The answer to that one is false. So you can kind of get the answer to that question. Doping, completely purifying. No, doping is the process of putting other stuff in, right? Athletes dope. They take different chemicals, steroids and other chemicals to help improve their performance. It's the opposite of purifying. So doping is the process of adding impurities in specific amounts and types to semiconductors so that we can really control them well and know when and where they're going to conduct electricity. And that's what allows us to actually make electronic stuff. So now I'm going to hit next. And here we go. Which of the four fundamental forces is the weakest? We already talked about that. That's gravity. Which force holds the nucleus of the atom together? We already talked about that. It's the one, remember, the nucleus has the two positive charges or multiple positive charges in the center being held together against their will, really, because they're positive charges and the electromagnetic force wants to push them apart. But the strong nuclear force is way stronger and it holds them together as long as they're at that close distance. So the force that holds the nucleus together is the strong nuclear force. Which of the following is a region around a charged particle or object within which a force would be exerted on other charged particles? So it is a region around, it's an area in which a force would be exerted. So an area is just going to be, that's the electric field. So the electric field is the area over which the electric force is projected. The electric force is the projection of electrical potential, and that actually becomes potential energy when a charged particle is put in the field and work can actually be done. Which of the following is the capacity of a charge to do work because of its placement within an electric field? The capacity to do work has to be energy, electric potential energy. Which of the following has a very large gap between the valence band and the conduction band, making the conduction of electricity very difficult? An insulator is what it has difficulty conducting electricity. That's the point of it, right? It insulates, keeps electricity from conducting. And so it has a huge gap between the valence, the top energy band of the atom, and the conduction band, which is the higher energy state that allows the free flow of electrons. Which of the following have essentially overlapping valence and conduction bands? making the free flow of electrons possible within the material. So that's conductors. Which of the following are doped? So we can precisely control when they conduct and do not conduct electricity. That would be semiconductors. Next, I think we have 3 more questions. Which of the 4 fundamental forces acts essentially over infinite distance, even though their influence is small enough it can be ignored? The 2 infinite ones are gravity and electromagnetism. If an atom is electrically neutral and 2 extra electrons are added, what is the net charge? So it's neutral and you add 2 negatives because electrons are negative charges. So it's neutral, you add 2 negatives and you end up with a -2. And I think we are at the last question. Here's the situation. A rubber rod is given a negative electrical charge. Come on, I want to draw for this one. Okay, so here's the situation. A rubber rod is given a negative electrical charge, and I'm just going to kind of draw this out for you. Oh, I shouldn't have put that in a line there. Too bad. So sad. So this rubber rod is given a net negative charge, and it is moved near a metal rod. I'll draw this one correctly. There we go. That's better. With a wire, here's the ground, with a wire connected to the ground. That's into the ground. So this negative, so the metal rod is there and it's neutral. The rubber rod is negative. So we've moved a bunch of, moved a negatively charged objects next to this neutral conducting. That's important, conducting. Remember that electrons can flow freely in this thing. So if there was no wire there, if that wire didn't exist and you push this close to the metal rod, okay, so this is the rubber one, I should label these. This is the rubber, this is the metal. And if you push that charged rubber rod with the negative charges, what would happen to all the negative charges over here? Well, it's a metal, so they can flow around freely. So all those, you're going to end up like this, right? The positive charges don't move because those come from the nucleus. The negative charges all move, so it would push them all over to the side, right? But here's the thing with a ground. A ground is just a giant thing that can take or give electrons without even feeling it, basically. So when you connect it to the ground, what happens is when you push this thing close and it pushes all the electrons away, it actually pushes all these electrons down through the wire into the ground. So you end up losing electrons. So a lot of those electrons get lost because they get pushed down into the ground. So you have less electrons. And then you cut the wire so the electrons can't come back. You cut the wire so the electrons can't come back. And then you move the negatively charged rubber rod away. They have never touched. No electron has left the rubber rod at all, but you manage to push the electrons out of the metal rod. So now the rubber rod keeps its negative charge just like that, but since you pushed a bunch of electrons out of the metal rod, it ends up with a positive charge, at least for a while, until the negative charges in the air or whatever start to land on it. Okay, so I gotta, there we go. All right, so let's read through these. The rubber rod will lose its charge. No, if it doesn't touch the metal rod, it won't lose its charge. Oh, so that doesn't get checked. Sorry about that. The rubber rod will lose its charge. No, the rubber rod keeps its charge. It's not a conductor. Whatever charge we put on it stays there, at least for a while, until the air rubs off. The rubber rod will be positively charged. Nope, we already said it keeps its charge. The rubber rod will be negatively charged. Yes, it started out negatively charged. It will end negatively charged. The metal rod will be neutral. No, it will not be neutral. We talked about it pushing all the electrons down the wire, right? The metal rod will have a positive charge. Yes, that is accurate because we pushed the negatives away down the ground and then cut the wire. The metal rod will have a negative charge. No, that is not accurate. This is an example of charging by conduction. No, when you conduct things, they have to touch each other. This is an example of charging by induction. We induced it. We put a force on it without actually touching. we induced the movement of those negative electrical charges down the wire and then cut it and left it positive. That's the bell, so I got to wrap this up. So the last two, the electrons in the metal rod will be pushed into the ground through the wire. Yes. The protons in the metal rod will be pushed into the ground through the wire. No, that is not true because the protons stay there. The protons are what make the metal the metal. The electrons can move. So that's it. And let's see, it says I'm finished and I did a good job. So I'm going to hit submit. And then it says my response has been recorded and I'm going to view my score. Hopefully I got it perfect. Oh, shoot, I missed. What did I miss? We better go look. Holy cats. Doping is, that's so funny because I said the right answer and I clicked the wrong answer. That is so me. That is so me. All right, so that's everything. If you listened to this, congratulations. I'm proud of you and you should be proud of yourself for taking the effort and the time to study before you retake a test. That's all I have. Bye.